Hello students, this is lecture 10 of MTH 201. In the last lecture we discussed equation of a tangent plane to a graph z equal to fxy, linear approximation to a function around a point and the concept of differentiability. So last time we discussed about this set of implications. So PD stands for partial derivatives here. PD exists and are continuous. This implies differentiability. So existence of partial derivatives and their continuity was defined as what is called C1 function. And by the definition of differentiability, differentiability implies partial derivatives exist. Now, I mentioned in the last video that uh, these reverse implications, meaning differentiability implies partial derivatives exist and are continuous, and partial derivative exist implies differentiability, both do not hold in general. So so let us discuss two examples where these converses do not hold true. So for the second implication, reverse implication that partial derivatives exist need not imply differentiability. That is part of problem set 5, question 1. So I will not discuss it here. But let us discuss an example where the function is differentiable at a point, but the partial derivatives exist and are continuous. This condition fails. So this is the example. Fxy is x square plus y square times sine 1 by x square plus y square when x and y is not are not both 0, that is you are away from the origin, and 0 when your function is 0 at this point. Okay. So you can easily compute the partial derivatives here, fx and fy, which are defined on all the points other than 0, 0. But if you compute fx at 0, 0, it comes out to be, so by definition, fx 0, 0 is limit h goes to 0, fx 0 minus f 0, 0 divided by h. Now f 0, 0 is 0, so you just get fh 0 by h. So if you plug in x equal to h and y equal to 0 in the function, you get this. Okay. Of course, are divided by h. So this is what you get. And this limit by MTH 101 is 0 because the second term sine 1 by h square is bounded and h goes to 0. Right? So if you look at fx x comma 0, okay, which is where this definition works. So if you put y equal to 0, what happens is the first term is okay, but the second term is actually unbounded for every x. Okay, so this there is a problem here. Okay, so fx x0 is unbounded. Okay, and hence fx is not continuous at 0, 0. So I should not say for all x not equal to 0. That's not true. I will make it precise in the PDF file. But what happens is as you approach uh, x equal to 0, this limit does not exist. Okay. So fx is not continuous at 0, 0. Similarly, fy is not continuous at 0, 0. Okay. However, f is differentiable at 0, 0. So in this particular case, fx and fy exist, but they are not continuous at 0, 0. However, your function, if the full function f is differentiable at 0, 0. So by definition, you want to look at this limit, right? So you can go to the last lecture and compare the formula for the limit for derivative to exist with this. So this is what you get. If you plug in all the values from here, this is what you get, and this goes to 0 because why does it go to 0? Because this term is bounded and this term goes to 0 as xy go to 0. So this is an example that the first implication, reverse implication, does not hold true. Okay, so now let us come to what is called chain rule. So chain rule is, you have seen chain rule in MTH 101, where you have two functions of one variable, you look at f composed with g, derivative with respect to x, that comes out to be derivative of f at g of x times the derivative of g at x, right? So that is what you know. Now we are going to extend chain rule to functions of more than one variable. So to start with, let z be equal to fxy, where x and y are functions of t. Okay. So note that z is a function of x and y, but x and y are also not independent. They are also functions of t. So therefore, you can write this function as f of xt comma yt. So x is a function. So saying that x is a function of t and y is a function of t. So if you compute the, now z is a function of t, right? When you plug in x as a function of t and y as a function of t, then z is function of t only. So therefore you have this total derivative of z with respect to t, that's equal to the partial derivative of f with respect to x times the derivative of x with respect to t plus the partial derivative of f with respect to y times the derivative of y with respect to t. So the general idea is you go inside, so you look at the outside function, you see how many dependent variables are there. There will be that many terms, okay, and then going one by one you will have partials of f times the corresponding partials or total derivative of the inside variables. Okay. Now here you have partial, here you have total d, because here f is a function of two variables, so therefore you have partial, and x and y are functions of t alone, therefore there is a total derivative d here. But this sum can be written as product of these two matrices. This matrix product notation is going to turn out to be quite useful. Now, let us extend this idea to functions of three variables. So, if w is a function of x, y, z and x, y, z are functions of t, then w would be f of x t, y t, z t. Now following the same rule, you will have three terms because now f is a function of three variables. So dw dt will be partial f with respect to x times x prime t or dx dt plus partial with respect to y of f times dy dt plus partial of f with respect to x times dz dt. Now this can be written in matrix form as this. So let us understand these matrices that you get here. So the first matrix is what? It's actually the capital D, right? The Jacobian matrix of the function f, isn't it? And this column vector is nothing but the total derivatives of all these three variables x, y, z with respect to t. So this is all partial derivatives, these are all total derivatives. Okay, now you can think about generalizations. If if you have a function of, let's say, n variables, you'll get n terms with such products. Okay. So now suppose f is a function from R2 to R, it's a function of two variables u and v, and g goes from R2 to R2 is a function of two variables x and y, which is defined as follows. Okay. So g of x comma y is equal to u of x comma y. So u is also a function of two variables and v is also a function of two variables. Now define h going from R2 to R as composition of f and g. Okay. So if you take f composed with g of xy, by definition that is f of g x comma y. But gx comma y is uxy, vxy, so you put it here. So now hxy is f of ux comma y comma vx comma y. So remember in the previous slide, this x comma y was actually t. So it was a function of one variable. Now it's a function of two variables. So there are two levels here that we have to see. Okay. So first of all, forget about this middle thing. So hxy is f of uxy comma vxy. So h is a function of x and y. Therefore, you will talk about partial derivatives now. So partial of h with respect to x. Now x appears here as well as here, right? Which means you have to differentiate f with respect to this and also with respect to this. So you get partial f partial u, right? Differentiating f with respect to u and then u with respect to x. But that will also be partial now because u is a function of two variables. Okay. Plus there is x term here, so you differentiate f with respect to v times v with respect to x. So this is what you get. Now mimicking this idea for the other variable y, partial h partial y would be partial f partial u partial y plus partial f partial v times partial v partial y. This is what you get. Okay. Again writing in matrix form. So what is the derivative, the Jacobian matrix of h? It's partial h partial x partial h partial y. But partial h partial x is this term and partial h partial y is this term. If you write it in matrix form, this is what you get. You get the derivative matrix of f times derivative matrix of g. Right, because G has two components, so it will be of two variables, so it will be a 2 by 2 matrix, right? The first row is all the partial derivatives of the first component, which is u. Second row is all the partial derivatives of the second component, which is v. So the first term comes out to be dfg of x comma y, because these are with respect to u and v, right? G, when you apply on G, you get u and v and times dgxy. So this is similar to what you have seen in one variable, right? So if h was f composed with g, then h prime was f prime at gx times g prime x. So it's the same thing. It's just that now you don't have scalars, you have matrices. Okay. Now let us look at chain rule in the most general setting. So let f be a function from Rm to Rp. So it has p components. Suppose the components are f1 through fp and the variables are u1 through un. And suppose g is a function from Rn to Rm. So there are n component g1 through gm. And the variables, n variables on which it is defined are x1 to xn. Now suppose g is differentiable at x0, which is a point in Rn. So it has n components, and f is differentiable at the point g of x0. So g of x0 will sit inside Rm. So Rm is what we need, because right, f's domain is Rm. Therefore, we need a point which is in Rm. So it makes sense. Now you define h going from Rn to Rp as h equal to f composed with d. This also makes sense because g starts on Rn, goes to Rm, and then when you apply F, that takes Rm to Rp. Therefore, H goes from Rn to Rp. That's how composite functions are defined, right? Then this function H is differentiable at x naught, and the derivative matrix of H at x naught is nothing but the product of derivative matrix of F at gx naught times derivative matrix of G at x naught. So you can, it's the same, the order is the same, it's just that instead of derivative you have the matrix, right? Now what is the size of DH? It's P cross N, right? Last time I told you that it's like linear algebra, linear transformations, right? So the size of DH is P cross N. The size of DF is P cross M, and the size of DG is M cross N, right? So all the dimensions match. So DHX naught is P cross N, DFGX naught is P cross M, and this is M cross N. So you can multiply these two and you will get a P cross N matrix. Let us look at this example. So X is a function of T and S, Y is a function of T and S, and U and V are functions of X and Y. So you can do one thing where you can substitute X as a function of T and S, Y is a function of T and S in both U and V. Then U and V will become functions of T and S, right? That's one way of looking at it. But let us use chain rule. Okay, so X with respect to T, for chain rule you need all the derivatives, right? Because you need all the derivative matrices. So you compute all the partial derivatives of X, Y, U and V with respect to their variables. In the second row, I have plugged in X to be a function, X as a function of T and S also, just to tell you that, that dependency is also there. Now, U and V as functions of T and S can also be written as I told you earlier, by just substituting X as T square plus X square, S square, and Y as S times T. And then you can compute these derivatives directly, right? You can compute UT, US, VT and VS from here. Now let us verify chain rule. So what does chain rule tell you? It tells you that when you compute U with respect to T and U with respect to X, that S, that is nothing but U with respect to X, U with respect to Y times the derivative matrix of X and Y with respect to T and S, right? This can also be seen like this, as we have seen earlier. So if you substitute everything in this matrix form, Ux and Uy are evaluated at X and Y, right? As functions of T and S. So Ux is nothing but 2 of T square plus S square. Uy is nothing but 2st, and these values are given here. So if you multiply, you get these numbers. But these are basically same as what you expect, right? From direct computation. Okay. So this is what you get. And similarly, you can check for V. This is for you. You can also check for V. Okay. Now let us try to use chain rule for curves on surfaces. So let f going from R2 to R be a differentiable function of two variables x and y, and let gt comma ht, where t goes varies over R, be a curve in R2. So you can see that in xy plane you have this curve GTHT. So what you do now is you just look at the image of this curve on the surface. z equal to fxy. So you will get a curve here. This is the curve, right? So a curve is given on R2, you look at its image under F. That will be a curve that is lying on the surface, right? So now you look at this curve CT, this curve, which is what? The x coordinate is GT, y coordinate is HT, and z coordinate is the image of this point under F. So it is f of GT comma HT. This lies on this graph, right, which is z equal to fxy. Okay. So the question is, what is the tangent vector to this curve at the point x naught comma y naught which lies on this curve? Okay. So it is, let's say this x naught y naught is the image of this point t naught. So according to this picture, this this is the point, right? At t equal to t naught, this is where you are. So what is the tangent vector? Tangent vector is given by g prime t naught. So you just differentiate this with respect to t naught, t, and evaluate at t naught. So you get g prime t naught I, that's the I component, h prime t naught, that's the j component, plus now you want to differentiate this with respect to t, so you can use chain rule. So it is partial of f with respect to x times g prime t naught, and where do you evaluate this partial derivative? At gt naught ht naught plus partial of f with respect to y evaluated at gt naught ht naught times h prime t naught. That's the last component. So the third component is nothing but k prime t using chain rule, where kt is equal to this function, right? So this you have already seen when we talked about chain rule 1, right? Okay. And this vector lies on the tangent plane to the surface at this point, right? Which is given by this. Because why? Because this curve is on the surface. So what is tangent plane to a point? It is a plane that is going to contain the tangent curves through that point of all the curves that lie. So this is one such curve, right? So this vector v, which is nothing but this derivative, should be lying on the tangent plane to this surface at this point. Okay. And why is this true? Because c prime t naught is orthogonal to the normal. What is the normal to the tangent plane at this point? This is what we saw last time, right? This is the normal to the tangent plane. So if you take dot product of this vector with this vector, it comes out to be 0. You can check that. Okay. Let us look at this example. Find the tangent vector to this curve where gt is et, ht is e minus t, and fxy is x by y. So the tangent vector from the previous slide is given by this expression. You just compute all the derivatives and plug in the values, and you get c prime 1 to be this quantity. So this is the normal, this is the tangent vector to the curve which is sitting on the graph at particular point t equal to 1. Finally, there are a few rules of differentiation. The first one is called constant multiplication. So if you have a function which is differentiable at a point and you multiply a function with a scalar, then the new function is also differentiable, and the derivative matrix is nothing but you multiply the old derivative matrix with that scalar. Okay. And here both sides you have m by n matrices, right? So when you say these two are equal, you are saying that two matrices are equal. Then you have sum rule. So if you have two functions which are differentiable at a point, then their sum is also differentiable, and the derivative matrix of the sum is the sum of the derivative matrices of the individual functions. Fine. Then you have product. If you have two functions which are differentiable at a point, then their product is differentiable at that point, and then you have this product rule. So you can understand it like in one variable where derivative of f times g is f times derivative of g plus f prime times g. It's the same thing. Instead of prime you have derivative matrices. So again these things make sense. Both sides you have 1 cross n matrices because these functions are from Rn to R because you're multiplying, right? So you can only multiply scalars. So therefore your range is R so that this product makes sense. Finally you have what is called quotient rule. So if you have two functions from Rn to R differentiable at x naught, and the second function, let's say g, is non-zero on all of the domain, then you can talk about f by g, right? Because this number will make sense because g is never 0. This is differentiable at x naught and the derivative matrix is given by this. Okay. Now this also you should understand like one variable. So derivative of h, which is f by g, is g f prime minus f g prime divided by g square. Now instead of f prime and g prime you have derivative matrices. Now on the left hand side you have a 1 cross n matrix. On the right hand side the numerator is a 1 cross n matrix and you divide it by a scalar. So dividing a matrix by a scalar meaning dividing each entry of that matrix by that scalar. Okay. So this is where we stop today's lecture.